So Athif Shaffy is a software entrepreneur and full stack developer who founded the Alpha Nova in March 2025 to deliver innovative digital solutions. Previously, he spent nearly 2 years at Maestro Digital Mind, intern to software developer, leading feature development and integrations, and held roles at the Con Alpine Information System 99X, Kelsey Technologies, and Trace Expert City, where he built and scaled enterprise applications. His early career included an internship with IBM's Watson team, developing AI chatbots and Node.js integrations. Atif holds a graduate certificate in mobile application development from Camden College and a bachelor's in software engineering from Staffordshire University, and it's proficient in JavaScript, Angular, and the Iconic framework. When you would like to start, we are glad to hear you.
Yep, you can hear me, right?
Yeah,
I'll
thank you.
share my screen. Yeah, I'm going to talk about one recent challenge that we did about identifying blast pattern in a mining company, and how this approach can be applied to any other computer vision challenges, I guess. So I represent the Alpha Nova. So some of my colleagues may be already in the chat. So we were a team that tackle this problem. So let me explain a bit about the challenge. So we got a bunch of videos from mining company, and they asked us to analyze if it is a good blast or bad blast, but we didn't get too much of information like what is a good blast and what is a bad blast. We didn't get any of those, and we were asked to figure out what makes a good and bad blast. So some from our research, we realized that there is something like fragmentation, dry rock, deflagration. So all of these matter to see if it is a good or bad blast. So and then in this video, we asked around a bunch of people, and they said a good blast is something like this, there is not too much of smoke going up, and then it goes in a sequence, so that is good blast. And then we generated an AI, like Sora generated a bad blast, some thing that is obviously bad, like it is going for uh, uh, the lorries and stuff. So what we did for this challenge was we collaborated with the experts. So our background was mainly software development, and we knew about machine learning algorithms, but we didn't have expert knowledge about the mining process, like how the blast system works and stuff. So we spoke with the experts. Like there's a company called Vipreg. They helped us a lot, and our teammates, we had some mining engineering consultants that helped us. And Lawrence University had a mining program, so we got a lot of help from there, and Cambridge College itself. And we spent a lot of time trying to quantify and our approach, and we made it in a way that our approach could be applied to any computer vision problems. And yeah so what we got from the problem was a bunch of videos, and then we got data points this is the blast design and stuff like that, and then they asked us to come up with a solution. So what we came up was so there are few factors that matter, like Bar's particle distribution ratio, and then fly rock. Like the name suggests, fly rock is when there's a blast, the number of rocks that are flying around. And if it is like a bad blast, there'll be too many rocks flying around. Deflagration is the color of the smoke. Like if the color is yellowish, then it means the explosive wasn't detonated properly. And confinement is when there's a blast, if the more it goes up, it means there's a lot of vertical confinement. And then if it goes horizontal, if it goes too much on the side, it is bad. So that affects the fragmentation. And misfire meaning uh, some explosive didn't get fired. So all of these factors, like we did research, like we used all the AI tools, I guess, like Notebook LM, Claude, all of them to like do our research. And when we spoke to some of the like Laurentian folks, they said all of these things they teach in like 2 years of mining engineering. So, and like for our challenge, we had to do it within months. So we had to use all the AI support that we could get. And coming on to fragmentation. So fragmentation means like in mining, if there's a blast, fragmentation is like how small the rocks are broken down. So if the rocks are not broken down into small particles, then it's hard to put it on the lorries. So, and you need to blast it again. So that means like you need to spend more money blasting the rocks again. And if you take the big rocks and put it on the machine, it's like lorries, then it will take more the increased wear and tear. So we had to optimize like the stemming meaning like the parameters for the explosive to make sure that it is good. So we came up with there is a model called Kuzram that like finds out based on the parameters you put for the like blasting, like for example like explosive size and stuff, how the fragmentation is going to be. So we since we got already the explosive, like everything, the blast is done and the videos, we analyzed the fragmentation from the Kuzdam model. And the next thing we analyzed was the fly rock. So for the fly rock, the fly rock is like we had to analyze from the blast if like how far the rock is flying. So the further the distance that the rock is flying, that means it's not good. Like explosives weren't added properly. So we had to do our like we did our motion tracking. There was a motion tracking algorithm that we used to find out like how far the distance goes, like from if we blast a rock, how far it goes. Then we map the trajectory, so from the initial point to how far it goes. So and then we mapped like based on the pixel how far it goes, and then we visualized it, and like we made something like this, the radius. So if there is if the blast radius is too high, that means the fly rock wasn't the blast isn't good. So we used computer vision like techniques to figure out like how far the rock goes, and figuring out like if the fly rock is good or not. And for misfire means like whenever on the earlier slide I showed about good blast, it has on a sequence it goes. But there could be cases where some of the explosives aren't blasted properly. So we had to we found a way to find the misfire that was like based on each of the frames we detect if there's any difference, for example everything from the initial frame to the end, we cross check each of the frames and we see if one of the frames is not in the sequence, we mark it as a misfire, and then we just get the count. If like from the frames, if we get like a lot of counts of misfire, we mark it as like there's a misfire and stuff. So for deflagration, this was a quite simple computer vision problem. We got a fume chart that says based on the color. So there's no fume. It's at level 0. So we used like computer vision to RGB analysis to find out which color is means it's good, and like if there is purple or red fume, that it means the explosive didn't go off well, and then the blast isn't good. So we used a simple like uh, RGB analysis to find this thing. And for confinement, we used a computer vision algorithm to see how much it goes vertically and horizontally, and we map that also in our approach. So all of these factors were resulting in if it is a good or bad blast. And then this was our approach diagram. So major things was like fragmentation. That means like how when we blast it, how small the rocks are. So for that we used BPST, that is the Kurzweil model, and then misfires. So if there's a misfire, that means the rock isn't blasted as well, as well. So we need to blast it properly. And then fly rock is how far the like particles fly from the original place of the blasts. So all of those contribute to the fragmentation, and then the color levels contributed to the deflagration, and then confinement. For the confinement, like if it is going horizontally or vertically, so uh, based on that angle, we found the that time the fly rock, like we used that again for the confinement to find the overall rating. So our rating, we added weights based on like what we thought was like, after talking to the experts, what we thought was I think like having more sense. For example, for fragmentation, that was we added the most weight for fragmentation because if the best outcome to to measure if the blast was good or not is based on the fragmentation, like how much small the rocks have been broken down. So we used the three methods to figure that, and then for deflagration, the color levels, and then confinement, the horizontal vertical angles, and the fly rock. And this was our solution video. So in the fly rock, we find like the number of rocks that have been flown away. This is the Kurzweil model, and this is the confinement. So from the misfire, we can see like which frames have got the misfires. This is to see the fume, the color of the fume. And then we give it an overall rating, like if it is a good or bad blast. And we give a recommendation, like which things to improve, and then we give them a report, like okay, this is the, and it's like this is what we find is like if it is good or bad and stuff like that. Yeah, that was it. And like this is a simple approach that like we could use for not only for the mining, but like any computer vision problems, we could apply the same approach, like figure out all the factors that affect the, like for example, if it is drone footage of in agriculture, we can get all the factors, and then we can like find the analysis and do so. I hope this was like giving some insights to like easily apply these approaches for other computer vision problems. And talking about the tools that we used, we use RoboFlow and like state-of-the-art technology like TensorFlow and PyTorch. Like some algorithms are working better on PyTorch, some on the TensorFlow model. So we use those, and we did a lot of labeling with RoboFlow, and then we got the models from that. That's all. That's it from my side. Any questions?